Hello and welcome to the AI Research Roundup. I am Alex and today is May 19th, 2025. We are looking at a paper from Hugging Face's trending list, Parallel Scaling Law for Language Models, published just 4 days ago. This research paper introduces parallel scaling, or ParScale, a novel method for scaling models by increasing parallel computation. It applies multiple diverse, learnable transformations. These are varied input adjustments the model learns, then runs the model's forward pass. It's core processing from input to output, in parallel for each, before combining outputs. The authors find this can offer gains similar to making a model logarithmically larger, but with much better inference efficiency. Building on that idea of parallel scaling, this first figure really helps visualize its advantages. It contrasts parallel scaling with traditional methods like parameter scaling, just making the model bigger, which costs a lot in memory, and inference time scaling, which adds to processing time. The charts then demonstrate that as you increase these parallel streams, the model's loss, a measure of its error, where lower is better, goes down. And importantly, parallel scaling achieves this improvement with significantly less increase in memory usage and latency, that is, the delay before getting a response, compared to simply enlarging the model. Alright, so this table offers a really clear comparison of mainstream LLM scaling strategies. It includes traditional dense scaling, just making the entire model larger, and mixture of expert scaling, a method using multiple specialized subnetworks. We also see inference time scaling, which aims to improve reasoning by using more computation during inference, often with reinforcement learning. The table highlights how parallel scaling achieves moderate inference time and space costs. It also offers flexible pre- or post-training options, without needing complex specialized strategies like load balancing or reward data, unlike some other approaches. This comparison really emphasizes its practical advantages. Okay, so moving to these next plots, we are looking at how model performance, specifically the loss, again, that is the error rate where lower is better, changes with model parameters and the number of parallel streams, which is P. The two graphs, for different datasets, show that as P increases from 1 up to 8, the loss consistently drops for various model sizes. This demonstrates that increasing parallel computation with parallel scaling improves performance, much like using a larger model, but with those efficiency benefits we talked about. The lines also represent a fitted scaling law, and the very high R-squared values indicate this law accurately describes the observed improvements. So, building on that observed scaling law, these next graphs really highlight the efficiency of parallel scaling. We are looking at how the model's loss changes with inference costs, specifically GPU memory in the top row and latency in the bottom. These comparisons are shown for different model sizes and batch sizes. Batch size being the number of data samples processed simultaneously. Blue arrows show traditional parameter scaling. Gray arrows represent parallel scaling. It is evident that increasing the number of parallel streams achieves similar loss reduction, but with dramatically smaller increases in memory and latency costs. For instance, requiring up to 22 times less memory increase and 6 times less latency increase to reach comparable performance levels in certain configurations. Alright, this table then details the performance of 1.8 billion parameter models, trained using a two-stage strategy with 1 trillion tokens. A token being a unit of text the model processes. We see scores across general, math, and code benchmarks. For coding, metrics like pass at K indicate the percentage of problems solved in K attempts. Notice how for parallel scaling, as P, the number of parallel streams increases from 1 to 8. Performance consistently improves, particularly on those more reasoning-heavy math and code tasks. This really highlights the practical gains from scaling computation. Okay, so building on those performance gains, this figure illustrates the efficiency of a two-stage training strategy. Stage 1 shows normal pre-training for 1 trillion tokens, where the model's loss, its error rate, decreases and stabilizes. Then, in Stage 2, parallel scaling training is applied for just an additional 20 billion tokens. The inset clearly shows that even with this relatively small amount of further training, increasing the number of parallel streams, P, from 1 to 8, continues to reduce the loss. This really highlights how parallel scaling can effectively enhance pre-trained models with minimal extra training cost. So, to wrap up our look at this research on parallel scaling, it is clear that this approach, which involves running multiple transform versions of an input through a model in parallel and then combining the outputs, offers a really compelling way to enhance LLM capabilities. The key takeaways are its remarkable inference efficiency, getting similar performance gains as much larger models, but with far less memory and latency overhead, and the new parallel scaling law, which quantifies how increasing these parallel computations boosts model capacity, especially for complex reasoning. Thanks for tuning into the AI Research Roundup.